Hi, Nora. Hi, Sunita. So,
Good
question.
evening, Professor.
Good evening.
Hi, Sunita.
Hi, how are you?
Good, thank you.
You're welcome.
Lovely.
I do have a question. It is about the negating and existential and conditional
Okay.
in the measure two material.
All right. Let me,
And, oh, I'm sorry.
no, you're fine. So I'll grab that. So this would be in the first document or the second document.
Yes, the first document, and I think it's on the first page.
Okay, great. All right. So which number?
I have it up. Let me just pull it up.
Me too. I've got it up too, so we can look at it together.
It's number 6.
All right, number 6. It says disprove the following statement, use the definitions, and you said you had some issues about negating that.
Um, I had two questions in particular. The first one was the use of P and Q to represent the conditions, because that was confusing to me because the first condition is that, let me pull it up again.
Yeah, I can see how this would be confusing because there's a lot going on with this.
That A, B, and C are all odd, but A plus B but A plus B plus C is even. And I didn't understand why you would use P to represent that A plus B plus that A, B, and C all have the property of being even, but that you used not Q or rather Q to represent that A plus B plus C is even. I would think, or it seemed to me that you would use P for both because they're both even, and then not P in the negation.
Right. Okay. Well, any way you slice it, the bottom line is that we have some rules for negating existential statements, and whether you call it a P and Q or call it P and not Q, it just doesn't really matter. Okay, so let's take a look. I need to also see this document. So the statement is, oh gosh, ice cream man is out. So on number 6, we have there exist integers. Will you read it to me?
Yes. Okay. There exist integers A, B, and C such that A, B, and C are all odd, but I'm sorry, I'm going too fast.
You're fine. But
A plus B plus C is even.
all right. So let's just parse this out before we even kind of dig in. So we have our existence part. This is our quantifier. And then such that, okay, with the property that here's our predicate, but it's a compound predicate, right? That A, B, and C are all odd, but means and, right? And then something about A plus B plus C being even. It doesn't matter. What would you like to call uh, A, B, and C are odd? Would you like that to be P of X or P of A, B, and C, or would you like it to be not P of A, B, and C? It doesn't matter.
P of A, B, and C,
And what would you like to call or name A plus B plus C is even?
not P of A, B, C.
Can't be not P because this predicate says more than just odd. There's more to this statement than just the word odd. It's talking about three different numbers being odd. Whereas this predicate does involve three numbers, but it's not saying that all three of these are even or that at least one of these is even or anything that's really that related to this, except that there's the word even instead of odd. This is about a single quantity being even. See what I mean? So we want
I
to use a
see.
different letter.
So that's why you used Q
Yeah,
of A, B, and C,
yeah,
because it's a completely different property.
yeah. Even though they
Uh,
both involve parity, talking about three different integers being odd, this is actually a compound predicate. This is the predicate P1 of A, A is odd, and P2 of B, namely B is odd, and P3 of C is odd. See what I mean? Like this is actually a compound component of a compound component, but it's easier just to say, okay, A, B, and C are all odd, and this quantity is even. They're really two different statements. Yeah.
okay.
So if we wrote it in formal style, right, you would use exist, there exists A, B, and C, and Z, such that, and here you can just write this out and then put an and between them and then just write that out. Or now that we know the name of the odds, we know that A, B, and C are odd. We could write as A, B, and C are an element of the set 2Z plus 1, right? That's like
Ah,
right? We know that now. You could write that A plus B plus C is an element of the evens 2Z, right? We know that now. Or you could
so
just write the phrase.
I had a question just real quickly. So this we're using the and. Does that mean that this is not an if-then statement?
It's a there exists statement. It certainly is not an
Oh, right,
if-then
right.
statement.
Okay,
Mhm.
okay. All right.
Now you might have an and in an if-then statement, or an or in the
Uh-huh.
hypothesis or conclusion of an if-then statement. And, compound statements can be nested or the components of compound statements can be themselves compound statements involving operators. But here, I think, remember there are different flavors of formality, right? As long as you put a there exists an A, B, C, and Z such that then you can either just write this phrase and maybe put an and in between that and this phrase, or you can write it like this with an and then this. See what I mean? There's different, the point is once we get it kind of sorted out, so it's this and this, however you write these two components, it makes it easier to negate it.
Uh-huh. And for the negation, the and would become a conditional arrow.
That's right.
Okay.
That's right. Because this becomes, of course, this flips to for all. But yeah, this is the negation of P and Q is that P implies not Q.
Uh-huh. Okay, that makes sense.
Does, doesn't it? Because then when you negate this back, it's the hypothesis and the negation of the conclusion, but not Q is Q.
And is that a way to kind of double check your work after performing a negation, then just maybe mentally negate the negation and see if you get the original?
Absolutely, especially if it's a
Okay.
tricky one like this.
Okay. I noticed that I struggled, especially in last class, with translating the informal to formal. And I noticed, if it's okay for me to just reference my quiz,
Sure.
um, I need to be a little more thorough with just memorizing, and it's not a difficult memorization because they're the rules are understandable. But for my quiz, I didn't fully express the definitions in their entirety.
Yeah,
And you mentioned that I overthought one
yeah,
of the questions.
that's right. Um, when we're writing the hypothesis or the conclusion, we want to just keep it simple and not dive into any of the definition stuff at that stage, when we're constructing our hypothesis. And then the next thing we do is we say, hey, what are we trying to show? What is our wish? At that stage, those very early sentences, we don't want to dive into definitions. We just want to just write the words. Then in the body of the proof, we dive into the definitions and walk up to the ATM and get our equations and things that we're going to use. Does
I
that help?
see. So,
Am I addressing actually the issue that you had?
yes, this is exactly what I need to talk about because I struggle with translating the informal statements to formal, and again with translating the formal statements to informal. And I think it's because I'm trying to say too much in the wrong place.
Okay, so can we look at that quiz together? Are you talking about the quiz that you just got back?
Yes.
All right, so let's take a look. And you're in section 102, so I'll share my screen. But both of the quizzes for this particular quiz were actually the same, but that's not certainly always the case. All right, so let's look at the solutions. Is that blurry? I'm not real happy with why that's blurry. Maybe it's just my eyes. Okay, so at what stage, when you're saying that when you tried to work problem two, you were writing it formally for yourself first?
Um,
Like,
for
where
number
were you
two,
writing something formally? You weren't asked to do that.
I know I get in my head and I start imagining I've been a scrambled mess, but I'm trying to get the right focus.
It's okay.
And
It's okay. It's part of the process, is learning how to kind of trim it down to something simpler. Let's look at this one together. Okay, can you just read that? I'm gonna write the statement down. Will you read it to me while I'm writing it down, and then we'll pop out of the share screen.
for number two,
Yeah, can you just read me the statement?
suppose you wish to prove the following statement using a direct proof.
Okay, keep going.
For all integers a and b, if a is even and b is odd,
Mm-hmm.
then 3a plus 2b is even.
All right. So it is an if-then statement, and we could write it formally, just to kind of make it a little easier. So it's for all A and B and Z, right? A even and B odd together imply that 3A plus 2B is even, right? Now that's sort of junky, but just for our own edification, we can at least realize, hey, here's the hypothesis P of A and B. Here's the conclusion Q concerning A and B. And it's a for all statement that's an if then as they all could be. So for direct proof, the thing to remember is even though this is universally quantified, when we write our assumption, we don't say all integers A are even and all integers B are odd, because that's simply not true. all integers A aren't even. It could be either one. But we want to represent an arbitrary even number with the letter A. That's kind of what we're doing. So there's a little something going on here. There's something subtle here. When we get ready to assume, it's really just this part. Assume A is even. Now, what this means is A could be any even number. So in some sense, we are discussing every even number, but A isn't every even number. It's just some unknown even number. We're not going to use anything special about A, like any particular value. We're going to use the fact that A is even, and we're going to use the definition of even. See what I mean? See the difference there?
I see.
A is a generic representative of even numbers. So in that sense, it represents all, but it is not actually every even number. It's just one even number. We just don't happen to know which one it is because we can't assume that it's a particular value. We have to prove what we're proving for any even number. So this is just some unknown even number. And B is an odd number. It's just some unknown odd number. See what I mean? That's what we assume. And you could say they're integers. If you want, you could say assume A and B are integers and A is even and B is odd. And that's not wrong. There's nothing wrong with that. However, when we say A is even, aren't we saying A is an integer too? I mean, like, isn't that part of being even? So we don't,
Yeah.
yeah, we don't even have to say A is an integer. Because if we say something is even, we know we're talking about an integer because we know we're talking about something that looks like 2 times an integer k. And 2 is an integer, k is an integer. So 2k is definitely an integer, right? So we don't even need to say A is an integer because that's sort of folded into the definition of even. It's not wrong to say assume A and B are integers and A is even and B is odd. But at this point, it's sort of a singular thing. This is some single unknown even number, A, and some single but not known odd number, B. And you can just assume P. That's what we're doing. We're taking P, and that's what we have in our hand. And if we need to say more, if we want to say they're integers, that's fine. What do we wish? What is it we're really going to try to do?
We wish to show 3A plus 2B is even.
Exactly. It's that simple. And that's it. These were the answers to those two 8-point parts of that question. It's just, in direct proof, we assume P and we wish to show Q. So it is really helpful to identify your P and Q.
So,
Go ahead.
uh, in our assumptions and our conclusion, we go directly from the argument we're analyzing. So we
Oh, there's
just
a
take
bunch
a,
in between. There's stuff
well,
in
yes,
between.
yes, but the definitions themselves don't come into play until we start to show how we move from the assumption to the conclusion.
Exactly. You don't, yeah, right. Like nobody wants to read this, some kind of hard, and it's really just that mathematicians, we don't want to get overwhelmed. We just want to know the simple facts, just the facts, ma'am. What do we really have? And then we'll break it down and break it down and build it back up and build it back up.
So for what we're looking at right now, after stating assume A is even and B is odd, it seems to me like the next thing that I would do is present the definitions of even and odd.
Let's do it. Let's go ahead and write the proof. By the definitions of even and odd, and I'll go to the next page. We have, well, you tell me, what do we have from the definitions of even and odd? This is this
We have
continued, right?
we have an integer a equals 2k, and where k is in the set of integers.
Good. K isn't great. K is in Z.
And we have the integer b equals 2k plus equals 2j
Yeah.
plus 1, where j is in the set of integers.
So why did you catch yourself and decide to not say A equals 2K and B equals 2K plus 1?
The repetition of k implies that they both have the same value, and that is not necessarily true.
That's right. Because if we used K here, we're saying B is the integer right after A. It's
Ah.
2K plus 1. In other words, we're saying they're consecutive integers, and we don't know that. And we're going to talk about consecutive integers tomorrow, so don't get worried about that. We're going to we're going to review. I can hear you think we're going to review that. Consecutive integers are, x, and then the next one is, x plus 1. And we don't know that. We just know that A is even and B is odd. Great. And now, shall we break our wish down a little bit and take a closer look at what we really need to do before we're done?
Yes, because now we can start to work with that um, argument or statement, 3a
Yeah,
plus 2b,
yeah,
because,
yeah. These are statements of fact now, and this expression 3a. That all right. So as it stands right there by itself, it's an expression, not a
okay.
statement. But if we say we want it to equal 2m, that is a statement. An equation is actually a statement. But then we could even add a little bit more and make it a little more interesting statement to complete our wish. And we're going to need to make m make sure m is an integer.
So, we state our definitions right out of our hypothesis.
Hmm.
So we define A and we define B, what it means to be even and odd. Now we can move on to express how this applies to our conclusion.
That's right. And one way I like to think about the wish is, geez, I want to say something smart about 3a plus 2b, what is it that I really need to talk about? Oh, we need to talk about 3a plus 2b. And that kind of gives you the inside track to saying, oh, okay, now I got to look at 3a plus 2b. Let's do it. What is 3a plus 2b now?
I wrote 3a plus 2b equals 3 times 2k plus 2 times 2j plus 1.
Great. And, seeing it like this gives us a chance to compare where we're at with 3a plus 2b with where we want to be, like expanding on the wish and having a very clear idea of what we need to show about 3a plus 2b helps us get from here to that, right? So we see, oh yeah, we got to get a 2 out front. So what do you do now?
I multiplied for 6k. I multiplied 3 times 2k. And then I distributed the 2 across the brackets, and I got 4j plus 2.
Sure.
and then I factored 2 out of all of this. So
Okay.
2 times 3k plus 2j plus 1.
And we can take a breath there. I need to take a breath. But it's a natural place to take a breath because we just showed that 3a plus 2b satisfies part one of the definition of even, right? There are two parts to the definition of even. The expression looks like 2 times something. And then in part two of the definition of even, we talk about how that something, whatever it is, it's like a big K, we're calling it M. We'll talk about how that's an integer. But right now we've got part one of the definition of even done.
I had 2 little questions. Um, I think so if I were to have written 3a plus 2b equals 3 times 2k plus 2 times 2j plus 1 equals 2m, that would have been wrong.
Um, yeah, because your reader isn't going to buy it because your reader
Oh,
has no idea what M is.
oh, that makes sense.
We call it M after we've figured out what it looks like. We don't call it M until we know that in the same breath we can say for sure M is an integer.
Ah, I see.
Does that make sense?
Yes, so by stating it before we show it, we're talking about something that the reader has no idea what we're talking about.
Yeah, it's not as it's called begging the question. You're kind of you're giving your conclusion without proper justification. But now we can
Um,
call this expression M and in the same sentence say why it's an integer.
well, I wrote M equals, I don't know if maybe I should have done it this way, but M equals 3k plus 2j plus 1, which by the closed property of integers for addition,
All right, I'm going to put a word in front of M because I don't want to start a sentence with a lowercase letter. So I'm just going to say let M equal that. Okay, see what I mean? Like sometimes short sentences are good. And now what do we know? We know M is an integer because why?
the closed nature of integers for addition,
And there's another operation in play.
the zero product property.
No, no, we're not dealing with a denominator that doesn't have to be zero, but
Oh,
multiplication is one of the operations that's in play to build this.
ah,
And the other thing you want to do is look at our proof money, okay? We want to spend all this money that we just got out of the math ATM when we cashed in on the definitions. We spent A equals 2K right there, right? When we substituted. We spent B equals 2J plus 1 when we put it in for B right there. What we haven't used yet is the fact that K is an integer and J is an integer. See, this is all part one of the definition of even and odd. This is part two of the definition of even and odd. We just finished part one. We used the part ones to get the part one done. We need to use the part twos to get the part two done. So we have to invoke the fact that K and J are integers because K is in Z and J is in Z and Z is closed under, you said addition
yes. And I
and
guess multiplication too.
yeah, and multiplication as well because we used both operations. Great. And now we have just kind of in two sentences, okay? But it's okay to say, because when we say that it's M here, that's fine. We're just renaming an expression. And then we go on to say M is an integer. If you just go straight from this to 2M, your reader's like, what the heck is M? So this is all part two of the definition of even, showing this expression is an integer, but we have to use this money here to buy it. We have, right? We know three is an integer. We don't have to say it. We know two is an integer. We don't have to say it. We know one is an integer. We don't have to say it. But K and J, it's friendly to remind your reader, oh, by the way, those were integers too. So what we're doing is legit. Does that make sense?
Yes. Um, I noticed that you pointed out the places where we defined variables, a equals 2k, b equals 2j plus 1. But then you pointed out the specific place where you use those definitions. So you're not just repeating them. You don't have a lot of the same terms written over and over again, like I do, and will correct before I submit. But
Uh-huh.
I'm just noticing that.
We try not to say the same thing over and over. And honestly, part of the process of of learning to write good proofs is going back and saying, I already said this. I don't need to say it again. So there's completeness and then there's elegance. You can be redundant and have a complete and perfectly logical proof, but we're actually eventually also shooting for elegance, which is a minimized but complete proof.
I see.
And if you like, it's always a good idea to go ahead and write that kind of wrap up sentence. What have we done? Just, it's kind of like, tell your readers what you're going to do. So we do that by setting up the proof with a hypothesis and saying what we're going to try to do. That's sort of like the preface and the beginning, right? Then you do what you got to do. That's like the body of the essay. And then tell them what you just told them. It's the closing paragraph, if you will, of the essay. But in this case, a little short sentence would do. Basically, this last sentence should look like the wish. So 3a plus 2b equals 2m, where m is in z, right? We've argued all of that. It equals 2 times m, and m is in z. And so we can just put it back in a little nutshell. So 3a plus 2b is even, by definition of even. Or just by definition. It's the only definition we could be talking about here, but you could say by definition of even. And in some professors, actually, I know some of my colleagues will make you say by definition of even. And if you don't, you lose a point, but that's fine. The point is a little summary. This is the last sentence of your proof. So this would have been a correct answer for the last part of this question as well. But I was accepting the wish as well.
Thank you. I really needed this.
So you always make our office hours very productive. All right. So Sunita, does this kind of get any particular questions going in your mind?
I'm just like checking the way,
Soak,
but
soaking
yes.
it up. Okay. Um, other questions then, folks?
The exam we have to like write all the thing like that.
Pretty much. Now, you can get close to full credit without writing all of this, but my recommendation is always write your wish. Don't ever not write your wish. Then you gotta apply the definitions. You gotta have equations like this. And it's polite to tell your reader where you get that stuff, you know? Kind of think like kind of think of it like you're telling a story to your 10-year-old nephew or niece, you know? You just want to keep it simple, but you don't want to leave out big gapes and gapping gapes. The reason that this is important is for you. It's not like it's supposed to be a chore. It's actually supposed to make your life easier. When we translate a statement like 3a plus 2b is even, into the actual equation that we see has to work out before we can say 3a plus 2b is even, this step helps you. It helps you realize what you need to look at next. And even though the definitions of even and odd are pretty simple, and you can probably get by without expounding upon your wish and writing the wish again, kind of more detailed, there are some definitions where you definitely want to expound on the wish because things kind of go sideways if you don't. Let me give you an example. Prove using direct proof.
Excuse me, Professor.
Yeah, sure.
I don't know if we'll have enough time, but could you just touch on mods? Just any amount would be great.
Well, then that's perfect time to ask. Why don't we do one right now? If A mod 8 equals 6 and B mod 8 equals 5, then AB mod 8, let me just see, how is that going to work out? I'm gonna change this to 7. Otherwise, I'm going to get a 6 again, and I don't want it. Equals 2. Like the way that this was phrased in the notes was find AB mod 8. Okay. But here I'm actually giving you what the answer should be, and I'm asking you to get there with a reasonable argument. All right. It's an if then. Are you with me? Will this help?
Yes, yes, very much. I was just going to ask really quickly because I remember the formula A equals DQ plus R,
Right,
where R is the 6 and the 7. So their remainders are 6 and 7.
right. So
Okay.
here's our fact. A mod D is equal to R means A equals DQ plus R, where 0 is less than or equal to R is less than D. This is an if and only if. So when you see that A mod 8 is, R is 6, and we see that B mod 8 is 7, we can translate these hypothesis facts using this fact into equations. And then to prove that A, B mod 8 is 2, we know we have to get an equation where it's AB equals 8 times some integer plus a remainder of 2. This goes both ways. We're going to use it this way, and then we're going to use it back this way. All definitions actually are two-way streets, even though traditionally in English mathematics, we only write the definition with an if. Definitions are actually if and only if statements. We say n is an even integer if n equals 2k, where k is in z, but that's really an if and only if. N is even if and only if n equals 2k, where k is in z. And it's simply a matter of style that we don't actually write if and only if. It's understood that when you're being told that you're being given a definition, that even though you're going to only see an if, it really means if and only if. It's one of the subtle things about the way we write mathematics. So in example 1, if we want to do a proof, what should we assume?
Assume A mod 8 equals 6
Mhm.
and B mod 8 equals 7.
We wish.
We wish to show A times B mod 8 equals 2.
Great. And in a minute, we'll expound on this wish using this two-way fact, okay? Let's keep that fact where we can see it. So we use that fact in two directions. Okay? Now, there are a couple of ways to dive in. You can say by definition of mod, or you can just say from our hypothesis, we know, or you could even say from our fact, we know, because I've been referring this as to that as a fact, and I don't mind if you do, but I'm just going to say we know. Well, what can we write? Because A mod 8 equals 6. We know, I'll go ahead and say it a little more, from our definition of mod, that what?
That A, that A mod D equals R is equal to A equals DQ plus R.
What's our D here?
D is the divisor. It's 8.
Uh-huh. So we're going to apply it. And then here's, one of our R's, and here's our other R. Okay. I'm just sticking them there. So A equals D, but D is 8 times, well, we don't know what Q is. We just know it's there, right? Plus what?
Plus 6
Yeah, plus 6.
R.
That is R. 6 is R.
Right,
I'm
right.
calling it R1, but it is. Where Q is in Z. Now I'm going to leave a little room between my Q and my element of Z, because in a minute we got to write an equation because we know B mod 8 is 7. What do we get from that?
B equals 8Q plus 7.
Now we've got the same issue that we talked about a few minutes ago. Do we know that the quotients for A and B are actually the same Q?
No.
That's right, because if we use the same Q, we're saying that A and B are actually not very far apart, but we can put a Q1 here for A. We can index our variables and Q2 here for B, and that works great just to distinguish those. Does that make sense?
Yeah.
Great. Now let's expand on our wish. See, what we just did was we used this fact from left to right. We had that A mod 8 equals 6, and we got an equation. And we had that B mod 8 equals 7, and we got an equation. So here and here, we're using the fact in that direction, left to right. But our wish is to get the left side of the fact. So we have to establish the right side is true so that we can go back and use the fact in this direction. So let's break down what it really means to say that we wish that AB mod 8 equals 2. What does that really mean, looking at our definition of mod?
That means A equals DQ plus R?
AB,
It means what we've defined as A and B? Oh,
but this is the product, AB. That's what I mean by AB. It's just A times
right.
B. What would we have to know before we could say AB mod 8 equals 2? We'd have to know that AB, now it's not A, it's AB, equals D.
DQ
But what's our D here?
8, but wouldn't we, well, for this problem, we only have one D, but if we had two Ds,
You
never
wouldn't,
mind.
you couldn't do it. You can't play
Okay,
the game with different divisors.
okay.
Well, I shouldn't say that. Of course you can, but there are certain rules of the game. The divisors have to have common prime factors, and the ultimate question or wish has got to be a question about one of those common prime factors.
Okay.
All right. But for now, we want to know that AB equals 8Q.
O equals 2. Plus 2. Plus
Yep.
2.
And now, since we're not actually using Q here or here, these are Q1 and Q2, we can just go ahead and use Q here.
So that's a different quotient.
Yeah, because these are three different variables. When we index two of them, they're different from each
Okay.
other. And then when you have one that's not indexed, it's different from the other two.
Okay.
It distinguishes them. Yeah. So look, the beauty of this is, hey, if we can establish that this equation happens, and we can argue that whatever Q turns out to look like, and it won't just be a single letter, it'll be some expression built from Q1 and Q2 and some numbers and some addition or multiplication, probably. If we can establish that AB looks like 8 times, something that's an integer plus 2, then we can use the fact in this direction because we will have established this. And then we get to go back and say, oh, by the fact in the other way, direction, then AB mod 8 equals 2. See what I mean?
Ah.
So this is our roadmap, and we're practicing using the fact in two directions. All right, so that's it. And it also tells us you got to look at A times B because we want to say something about AB mod 8 equaling something in particular. So we got to check out AB and see what it looks like when we factor out an 8. We're looking for that leftover to be 2.
I see.
Okay, so let's take a look at AB and that's the other beauty of expounding on the wish. It really points you right to what you need to start hacking away at. All right, so what is AB?
It's the two expressions that we found, AQ1 plus 6, 8, excuse me, Q1 plus 6 times 8Q2 plus 7.
Right. So this is where we're at. This is what we want.
Ah,
So now we're looking, oh, we're going to have to pull an 8 out, and hopefully the leftover remainder will just be plain old 2. So what can we do algebraically?
well, we can pull 8 out of both of those factors. I don't, I don't remember the word for those
This
expressions.
is a factor. This is a binomial factor. This is a binomial factor. They're called binomials because they have two parts that are attached with a plus or minus, as opposed to
Okay.
monomial, like AB is a monomial. Even though it's got two parts, they're attached with a multiplication or division. So that's just one term.
Okay.
This is a binomial, has two terms. 8Q is one of the terms, and 2, which is 2 times 1, is the other term. But we cannot factor an 8 out of 8Q1 plus 6 because we can't factor an 8 out of 6.
I remember you did something in class with the 6 itself
Well, we're
and
going to
produced.
multiply this whole binomial times this. Do you remember
Oh,
how to FOIL?
yes,
We're FOIL.
yes. I would 64 Q1 Q2
Yep, we're multiplying the firsts together to get 8Q1 times 8Q2 is 64 Q1 Q2. Then the outers, you know,
plus would
mm-hmm,
be uh 56 Q1
good. And then
and
I's
then
for the inners.
inner would be 48 Q2
Nice. Not 42. That would be 6 times 7. It's 48 Q2. Good. And then the last.
Would be 42.
Great. Now we've got a shot at pulling an 8 out. But what you might remember from class is this is way too big of a leftover to be a remainder when we're dividing by d equals 8. So we
Oh,
have to apply the QR theorem to this as well because we want to break this down so that the leftover turns out to be 2 if we're lucky.
we didn't. I remember in class you set up a range for the, I don't know, I think that the R value had to be greater than 0 and less than 8. Well, for this, I think it's supposed to be.
Yes, in fact, we want to get 2. But that's
Oh,
exactly right. The range for the R value is like if we're dividing by D equals 8, we don't want the remainder to be 8. That means
right,
we didn't pull out as many copies of 8 as we could have, right? So we want
right,
R to be between 0 and I guess 7. Yeah, would be the largest remainder when D is 8. And here we're shooting for a very particular remainder. We're actually told what the answer is, and we have to show how to get it.
right.
And
So,
class, you weren't told what the answer was. You were just asked to find it. But you asked, I wanted to write another proof one, and you wanted mud, and this is what I came up with.
so we look for how many times 8 goes into 42.
Yep. And so I'm just going to rewrite, as tedious as it is, I'm going to just go ahead and rewrite these other terms.
I
So,
remember in class you mentioned the big number, like a plop of numbers.
yeah, glop,
But
glop,
what
yeah.
we're looking for is the term that does not have uh you were just talking about binomials and I remember trinomials, but they have an order.
Don't
So it
worry,
would
you're getting
be
way off in the weeds there.
oh, oops, sorry. But what I was going to say is that the final term, the 42 that doesn't have a Q value, that's the far term is our remainder.
Right. That's right. Usually we write it that way. We do usually write the constant terms. Those are the terms that don't have any letters attached to them, at the end.
Oh,
But the point is, the first thing that we did when we were playing mod and div games was we practiced finding the DQ plus R form for a bunch of numbers. Remember, if you go back and look at the example one or whatever it was when we played mod and div games, we did a whole bunch of them. Here, let me see if I can show you. And so we're kind of trying to lean in on on that. Let me escape out of there. Let me just show you what I mean. See right there? Remember when we did that first? And we were just
yes.
practicing breaking down like 99 with D is 2. We wrote 99 equals 2 times 49 plus 1. 37, D was 5. We broke it down to DQ plus R. Negative 37 equals D times a different Q plus a different R, right? So we practiced that. And the reason we practiced that so diligently is because now we have to use that practice and break down a remainder that's too big. So let's just play the game. D is 8. We need to find the Q and the R when we try to break 42 down by dividing by 8. D is 8. So what is our Q and our R here?
Our Q is 5 and our R is 2.
Ooh, now we're talking because ding, ding,
Oh.
ding, 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 ding. Right? That's kind of what we were hoping for. All right. So I'm afraid that's too crowded. If somebody looks at that, they're going to be like, what is all that nonsense? Let me see if I can rewrite this. And now we can pull an 8 out of everything else. Let's do it. Because that's what we got to get, right? We got to get AB equals 8 times something. It's going to be like the big Q, right? Plus a 2 that's left over. So yeah, we have an 8 in every single term, don't we? First four
So
terms.
it would be 8Q. Oh, right. Q, right. Q1, Q2 plus 7 is that no, is that right? 8
Yep,
times
Q1. hmm
plus
Right, it was the other factor here. In fact, when we do this, we could just write 8 times Q1 times Q2 plus 8 times 7 times Q1. Like you don't actually have to calculate this. You could just write the factors multiplied together and then it's easier to pull them out. But anyway.
6Q2
Uh-huh.
and 5 plus 2.
And now we use this is an integer. That's our Q. Since So we haven't actually used the fact that Q1 and Q2 are in Z, right? But we can use them now since Q1 and Q2 are in Z and Z. We could write it a different way. We could write sums and products of integers or integers just for a little variety. Try to write these both ways so you can pick. If you can WebAssign, they say sums and products of integers or integers. Q equals 8Q1, Q2 plus 7Q1 plus 6Q2 plus 5 is an integer. I didn't quite have room to put element of Z here, which would be my preference, but I would never split a statement like that across two lines. Like I would never put element of Z here.
Oh,
I never. That's like a huge no-no. All right, great. So AB equals 8 times Q plus 2, where Q is an integer. Do you agree? It's okay to put this part on a different line. Now we've got that AB, not just A, but AB equals 8Q plus 2. And now we can use the fact in this direction and say that's exactly what it means to say AB mod 8 equals 2.
ah.
Maybe I call it fact, but it's really the definition of mod, isn't it?
Is that the same as the quotient theorem?
Um, well, no, but it's got a big piece of it that comes from the QR theorem, the quotient remainder theorem. Like this is a huge part of the quotient remainder theorem. The quotient remainder theorem talks about these two expressions, this equation and this double inequality, and it tells us the circumstances under which we are guaranteed to get this equation and this double inequality. This is a definition for the mod function in terms of the guaranteed form that the QR theorem grants us. See
Uh,
yeah, let's go back and look at the QR theorem. This is actually a really good question that you're asking. The QR theorem is an existence and uniqueness statement. Let A be an integer and D be, I should have just said D be a positive integer because if it's in Z plus, it's not 0. So that was silly. But anyway, so we've got an integer A and we've got a divisor that's strictly positive. There exist unique integers Okay, so that's a big fat guarantee. It says there do exist integers Q and R, and they're unique. They're the only ones that will work given a particular A and a particular D. So it's an existence and uniqueness statement, which is a big deal in math. There exist unique integers Q and R such that we get this equation, this relationship between A and D, and R has bounds. The remainder won't ever need to be too big. So the QR theorem is a guarantee that we can write A in this format using the divisor D with a bound on the remainder. When we define the mod and the div functions, we're leaning in on the fact that if we have an A and a D, the QR theorem guarantees us that A will equal DQ plus R for an R that's the correct size range, in the correct size range. See what I mean? So we're defining
Um,
div and mod in terms of this promise that the QR theorem affords us. We're going to see another theorem. We're going to see something called unique factorization theorem tomorrow in class. And I think you'll like it because it's another kind of guarantee. Theorems guarantee that we get certain results under certain circumstances. That's why mathematicians like theorems. Because once we've proven a theorem, then it goes into our memory banks in our toolbox as things that we may assume without proof because we've already proven them. And then you get the big old fat toolbox full of good results. And that's how big, important things get proven, is because giants stand on the shoulders of other giants until they have reached Mount Everest. Did you hear about the guy that proved Fermat's last theorem some years ago?
No.
He literally worked on it secretly for 20 something years. Literally a British guy up in his upstairs office, tiny cubby hole, and his wife would literally bring him tea and biscuits, sandwiches. And what he did was he leaned in on a bunch of results that have been obtained fairly recently in the world of mathematics in an area of mathematics called elliptic curves. And we actually have, and he used elliptic curves to prove Fermat's last theorem, which was an open question for hundreds of years. Lots and lots of people tried for a long time to prove it.
Wow.
And he did it. There were a couple of errors. There were only like this many people in the world that could even read his proof at the time. And there were a few, little corrections and, a couple of things but it was fixable. And yeah, he, it was his dream and he achieved it.
That's really cool. Oh, thank you, Professor. I really appreciate this.
I'll post
This,
the notes. You're so welcome. You're always very welcome because if it wasn't for you, we wouldn't have office hours with interesting questions, as often, for sure.
well, I'm going to try to get my proof portfolio submitted. If not tonight, then early tomorrow. So,
I need to get those links up. I apologize. I apologize. Those links should be ready to go. And I'm doing the best that I can. It's not very good. I need a vacation from my spring break vacation. Oh, I'm gonna
Have
start.
a great evening, Professor.